All right, here we go. Lesson 2.2, Compound and Independent Events. In your textbook, you will find this on page 38 of chapter 2. Here's kind of our 4 big ideas. Number 1, understand how to find and calculate compound events. And compound means, maybe we should add this here, more than one. How to find these probabilities with replacement and without. Understand what it means to be independent in terms of events, and understand how to compute or calculate probabilities with independent events. All right, well, here we go. What do mathematicians mean by a compound event? So here's kind of the definition. When it has more than one stage or part to it. Make sure you get that into your notes, okay, for compound events. Examples. Let's say you draw a card and then you draw another card from the deck without replacing it. Choosing a car dealership and then choosing a car to purchase, because the car that you purchase depends upon where you bought it from. Okay? Rolling a die and then rolling it again and again. This is an example of an event that has more than one part. Deciding whether to go to the homecoming dance, and then deciding what to wear. Deciding on a dorm to live in, then selecting a roommate for your freshman year, or finally, like tossing a coin 5 times. Each of these examples we kind of need to work through very carefully. So when those parts of an event occur, sometimes the first event influences how the second part happens. And sometimes the outcome of one part of the compound event will change the probability of the events in the compound events. So, individual parts of a compound event might not influence one another. This, by the way, is what we would call an independent event. And this is what we would call a dependent event. So make sure that this is part of your notes. Again, we know what compound is. It's more than one event. If those events do not affect each other, then we call them independent. Whereas if they do affect one another, then we call them dependent events. Quick example with a deck of cards. What is the probability of getting an ace with replacement and then without replacement? What that means is that we're going to pick 2 cards and then we are going to put 1 card back after every time that we pull it out. So with replacement, well, there are 4 aces. Okay? Again, we could say that there are 4 out of 52. We know that that reduces to 1/13. Again, if I find another, that would be times, we need to multiply those 2 things together. So times 1/13, which would be 1 over 169. Now, if I didn't replace them, meaning I took one out and then I looked for another one. Okay, so the first one, it's going to be 1/13, but the next one, there's no longer 4 in the deck, so we would say there's 3 aces left in the deck, and because I've taken 1 card out, there's now 51. So now we would take 1 times 3, I get 3, and 13 times 51 my calculator says is 663. And that's going to reduce down to 1 out of 221 times. So it's a little better when you have, it's harder, I should say, with replacement than it is without. So again, for an ace, these times I won't multiply them out, I'll just show you what the probabilities are. Again, there are 4 of these, and there's 4 of those. So it's again 1/13 times 1/13. And here again, without replacement, it's 1/13, and then because you've taken 1 out, it is now 3 out of 51. So they would be the same. Now for a red, that's a 50%, so that's 1 out of 2, times a black, 1 out of 2, that would be 1 out of 4. What about for without replacement? Again, for the first, it's going to be 1/2. Now for the next one, for the black, yes, we now have 1 less card in the deck, but we still have all the black cards in the deck. Yeah, so that would still be 26. Okay, again, we choose a red, then we choose a black. Red, red. Well, now again, with replacement, because we throw them both back, it's the same, 1 out of 4. 1 out of 2 for the red, but now for the second red, because we've taken 1 out already, that means it's no longer 26, but it's now 25. So this would be 25 over 2 times 51, which I think is 102. So there's my probability. Spade, that would be 1 out of 4. An 8, now be careful, we better go down, oh, that again, with replacement, we can just ignore that. It's going to be 1 out of 13. So that would be 1 out of 52. And a spade again is 1 out of 4 times an 8, because we've taken out a spade already, the 8 of spades is now gone. And so instead of 13 cards left, instead of 8, 4 of those left. Oof. I don't think we can do that one. We haven't learned the skills yet. Let's ignore this one for now. Okay, you won't get this problem. All right, moving on. Here's a simpler problem. Noah, 8 different hockey sticks to use for games. And 5 of those sticks have black tape, which means 3 don't. So the question becomes, he's headed off to the game, and we want to know what is the probability that neither of them are wrapped. Yeah. So again, 3 aren't wrapped. He has 8 different sticks. Now again, because he doesn't put it back in, he's already pulled it out, he's grabbing his second stick. Again, we assume that he has picked one that's black with tape. So there's 2 left, and then there's 7 sticks in there total. So this would be 6 out of 56, which reduces to 3 out of 28. I'm going to skip this one. Let's go to Halloween. It's coming down the pike here. October's almost here. My kids are excited. I don't know about you. What is the probability that the first 3 pieces distributed will all be Milk Duds? Good thing these are all wrapped candies. All right. So the probability of Milk Duds, we have 10 Milk Duds in, and we have 40 pieces. But we reach in there the second time, and there's 1 piece left. And since we're looking at the probability of picking 3 Milk Duds, that means the second one, there's 1 less, so there's 9 times 8 out of 38. Again, we multiply these together to find the total probability. I can do some simplifying here, for example. That would be 1 and 4. 8 and 38, that goes to 4 and 19. And the 4's cancel. So it looks like my final answer is 9 out of whatever 39 times 19 is. 39 times 19 on my nice calculator, 741. All right. If you reduce ahead of time, it kind of makes your life a little bit easier when you're calculating these out. If you were to actually change that to a percent, you would take 9 divided by 741, and you'd get about a 1% chance. So 1.2% chance. Not good odds. All right, we've got 8 balloons. 3 of them are marked with a W, and you got 3 darts. So what is the chances that you randomly hit 3 balloons and all of them are marked as winners? All right. Again, the first balloon. So there's a total of 8. You hit the one of the 3. So there's one less. One less balloon, one less W. One less W, one less balloon. Hopefully you're getting the idea here that we need to multiply. Again, we can reduce before we multiply the 2 and the 3 times 2. Those all cancel each other, so I've got 1 over 56. So it's almost like a 2% chance of that occurring. If you are shooting randomly, that is. All right, in this case here, we don't know how many balloons, we don't know how many candies, all we know is a percentage. 12% of the world is left-handed. It's roughly somewhere between 10 and 12. Now the first question to answer then is, well, how many are right-handed? Well, there are people who are ambidextrous, but let's kind of ignore that for now. Let's assume that the rest of the world is right-handed, so that would be 88. So what is the chances of randomly selecting 3 people and they're all 3 left-handed? So the first one would be 12%. Again, you could write 0.12 is probably the easiest way to do it. Like the second person is 0.12 and the third one is 0.12. Now, technically, these 2 numbers here have gone down because you've removed people from the world population. But because the world population is so big, the fact that you removed one of them isn't going to change the overall percentage. So the simple way of doing this is to take 0.12 to the 3rd power. And my machine says 0.12 to the 3rd power. This is not a big number. This is 0.001,728. So it's a 0.1% chance. Now, what is the chances that all 10 people will be right-handed? So again, if I look at the chances of a right-handed person, that would be 0.88. Again, I'm multiplying it out 10 times. That takes a long time. So instead, we're just going to say 0.88 to the 10th power. 10. And that is approximately 27.9% if we round it off to the nearest tenth of a percent. ACT. This is a thing that most juniors take during their junior year. And about 3% end up not taking it. That was my little note. I should be headed to bed. So if we have 5 juniors randomly picked, what are the chances that all will be taking the test? So the first thing you need to know is, what is the chances a junior takes the test? Like in the last problem, let's find out what the percentage is of the ones that will. So if we take 100, right, minus 3, that gives me the 97%. All right, so if I got 5 juniors, that means the first junior, 0.97. The second junior, 0.97, all to the 5th power. Again, there's so many juniors around in the US that the fact that you take one out, even though it does cause the total to go down, this is such a large number that taking one out is not a big deal. So 0.97 to the 5th power is about 89%, or sorry, 86. Yeah, so an 86% probability that all 5. And that none of them will be taking the test. If you take 0.3, whoop, that is a classic mistake there, people. 0.03 to the 5th power. We're going to get something really close to 0. In fact, it's going to be so close to 0 that, yeah, this is very close. We'll just say approximately 0%, even though it's not technically. Okay? So, this lesson 2, we've been talking about compound, more than one event occurring, and then independent, these two events that don't influence each other. So you roll a dice. What is the probability of rolling a 5 on both rolls? Is that compound? Is that independent? Again, 2 rolls was the key thing here. So yes, compound. Independent. Does one die know what the other die falls? No. This is, sorry, these do not know each other. So yes, they are independent. Okay? It'd be cool if you could teach die to know what the other die fell, but you really can't. All right. 4 students left to give their speeches. 2 are going to be chosen today. What is the probability that Jerry is chosen first? And then Ashley. Well, Jerry's probability is 1 out of 4. What is the probability for Sierra? Well, Jerry's now out of the picture, right? And so Ashley is 1 out of 3. So the probability that it's first Jerry and then Ashley is 1 out of 12. All right. Let's keep going to some other examples here. Oof. Well, here's our problem set. Off you go, yeah? 1 to 13 and 19, and I think it's on page 43. Again, notice if they are compound, if they're independent or dependent, and notice if there's replacement or not. Okay? Best of luck as you do these problems.